Hey everyone, Mr. Ahmed here. Hope you're doing well. I'm making this video here because I had this question come up a few times by email from a few of you, so I just thought I would make a video and go over this with you guys. Uh, Now, this question seems simple enough. It's actually quite deceptively simple. Determine an equation for the line through the point 0.35 that cuts off the least area from the first quadrant. So this is clearly an optimization with calculus question. As soon as you start seeing things like least or the greatest or a maximum, a minimum, you're essentially going to be using some form of basic calculus to arrive at the answer. Now here, what we've got is an equation. And that equation represents a line, obviously. That line goes through the point 0.35, and we want it so that that equation, or that line rather, cuts off the least area from the first quadrant. So maybe let's just draw that and maybe start kind of getting a feel for what this should look like. So here's the first quadrant. You've got the point 0.35. I'm not going to be too precise with that. So you've got the point 0.35, and you've got a line that is going to be cutting across or through this point, and you want it so that the area separating, or rather the area that the line cuts of the first quadrant is as small as possible. Okay, so already you can start thinking, well, is my line going to have a positive slope or is it going to have a negative slope, right? And logically, the equation of the line should have a negative slope, right? Because then you can have an actual area, or you can get a quantity for this area right here, and you want that area to be a minimum. If your equation was a positive slope, then technically that area goes up to infinity, right? Because as that line rises and keeps rising forever, well, so will the area, right? So then having a positive slope here doesn't make sense. Having a negative slope is the alternative here. So this has to be negative. Okay, so sorry, I'm writing with my what's it called, mouse. So it's going to be taking a little while. Okay, so we know that the slope is negative. Okay, that's cool. We know that, for example, let's call this point, this x-intercept, let's call it C0. Okay, and let's call this point right here 0, D. Okay, now in a second here, we'll see why this is really relevant, like knowing or at least attributing values, or rather not values, attributing variables to the x-intercept and the y-intercept is actually very, very important. Okay, but we'll get to that in just 1 second here. Now, we're going to say that our slope is m. Okay, we've already established that that slope is negative. Okay, we also have the slope point form of any line on a graph. Okay, and that's y equals mx plus b. Okay, slope-intercept form, my mistake. The slope-intercept form of is the equation of a straight line on a graph. Okay, where b represents the y-intercept. Okay, now what we can do here is, because we already have a point, we can start kind of generalizing and maybe start to, I guess, create the equation of this line. Okay, we don't have enough, right? We only have a point, we don't have the slope, so that's kind of what's missing here. Okay, so what we can start by doing is we can say, well, we know that when y is 5, x is 3. Okay, so that's how I'm going to start off. I'm going to say, okay, well, when y is 5, I don't have the slope, okay, but I do know that x is 3, okay, and that plus b. Okay, now the reason that this is nice is that because now I actually have an equation for the y-intercept of my line. Okay, I know that the y-intercept is going to be equal to 5 minus 3m. Okay, and the cool thing is that I can then take this and then plug it back into this equation here, and then now have an equation for my for this line where my only unknowns are going to be m, x, and y. Okay, so that's what I'm going to do. I'm going to take y equals mx plus b, and in place of b, I'm going to plug in this new expression for b. Okay, so here I have y equals mx plus 5 minus 3m. Okay, so far so good. Now, obviously something is missing. Like we need to figure something out for m. Like how are we, like what's going on? How do we go and about getting m, right? So that's the question. Okay, because once you have m, you've pretty much got the answer. Okay, but getting m is actually going to take you quite some time, and this is where the x-intercept and the y-intercept come into play, and why we attributed variables to these. Okay, now you've probably noticed that the area that is cut off looks like a triangle. Okay, so the area that's cut off is a triangle. And you know that the base of the triangle here is equal to c, right? It's going to be equal to the value of the x-intercept. You know that the height of the triangle is equal to d, which is the value of the y-intercept up here. Okay, so that means that the area of my triangle, well, you know that the area of any triangle is the base times the height divided by 2, right? So here the base is going to be c. The height is d, so c times d divided by 2. Okay? Now, this is where you're like, okay, so this is starting to be interesting because now we have the equation for the area and we want the least area. Okay, so this is the minimum that we want, and it's actually going to be to this equation once we kind of develop it a little bit more. It's going to be to this equation that we're going to apply our knowledge of calculus, okay, in order to determine the minimum value of the area. Okay, now what can I do here? Well, I do have this equation, so that could be useful, and actually it will be useful. Now, the reason for that is that when you look at what we have here, okay, we have C0, so we have an x value and a y value, okay? We could plug that into this equation and come out with an equation for C where our only unknown is m, okay? We can do the same thing with 0d, okay? We can plug it into our equation for the line and come out with an equation where the only unknown is going to be m, okay? And maybe that's kind of like throwing you off and you're like, okay, wait, what are you talking about? Let's just do it, okay? And you'll see what I mean, okay? So at C0, okay, so at our x-intercept, we have, and this is where I'm going to take the equation that we made for our line so far and plug in c as the value of x and 0 as the value of y. Okay, so maybe I'll just rewrite the equation down here. Y equals mx plus 5 minus 3m. Okay, now as I just said, y at our x-intercept is equal to 0. And the slope, well, we still don't have that, right? We'd like to have it, and that's kind of what we're hoping for. Okay? Now, x, we know, is equal to c in this case, or at this certain point, it's equal to c. So this is where I replace x with c. And then plus 5 minus 3m. Okay? And, well, the next step now is just to isolate c, right? So what I'm going to do is I'm actually just going to keep the MC on one side, but if that's okay with you guys, I'm just going to write it over on here. Okay, so MC equals, okay, and I'm going to send these two guys over, okay, the plus 5 and negative 3m, so I'm going to have that equals 3m minus 5. Okay, now the last step here to isolate c is just going to be to divide by m on both sides, so I end up with c equals 3 minus 5 over m. Okay. So hopefully this is starting to kind of make sense to you, and hopefully this is starting to help you to see how this is going to be relevant to developing this equation right here. Because the issue here is that we have area equals c times d over 2, and we have two unknowns, right? But we'd like for this to only be one unknown, and that's why we're expressing c as a function of m, and that's why we're about to go and express d as a function of m, and then I'm going to take those two expressions, which are c and d, I'm going to multiply them together, I'm going to divide them by 2, and I've got the equation for my area, and then we're going to apply what we know about calculus. Okay, so let's do the same thing here. So at d, or nope, sorry, not at d0, at 0d. Okay, so at 0d, we have, okay, well, we're going to use the same equation again. So y equals, I'm going to just write it out again, just to make sure I don't make any mistakes when I'm replacing the variables and the values. Okay, so there's our equation. Okay, and now I know that when x is 0, y is d. Okay, so here I'm going to say, well, d equals, okay, so I replaced y with d. M is still m, we don't have that, but we will. X is 0, because we're at the y-intercept, plus, and then 5 minus 3m. Okay, so d is just equal to 5 minus 3m. Okay, so this is awesome, because now I can express my area, or the equation for my area, using only one variable or one unknown. Okay, so I know that that area is now 3 minus 5 over m times, okay, and then now the expression for d, 5 minus 3m, and all of that over 2. Okay, so let's go ahead and maybe expand this and then simplify it as best as we can, because we know that what's coming up is we're going to have to determine the derivative of whatever this equation turns out to be. Okay, and the reason we're determining the derivative is because then we can determine what are the critical points. Okay, and once you have the critical points, then you can determine what is happening at those critical points. Is that a minimum value, or is that a local minimum, or is that a local maximum? Okay, and if you identify what the, well, local minimum or local maximum is, we'll see in just a second here, then you can pretty much, well, like, determine, well, okay, then that's, like, I know what's happening here. Like, this particular value of m is yielding me either a minimum or a maximum. In this case, obviously, it's going to be a minimum. Okay, so it's yielding me a minimum, which is what I want, right? So because we want the area to be a minimum. Okay. All right. So let's expand that equation first. Okay, I don't want to lose you guys too quickly here. So let's expand the equation. So the area equals, okay, so just expanding this guy here. Okay, the area is going to equal, well, 15 minus 9m minus 25 over m plus 15. All of that over 2. Okay, I'm going to keep simplifying. So that means, well, I'm going to put the 15s together. Well, that means 30 minus 9m minus 25 over m. And then that over 2. Okay, let's keep going. We're not done just yet. We will be soon. So that's equal to, well, 15 minus 9 over 2 m minus 25 over 2 m. Okay. Now recall that this is the equation for the area. Okay. Now I'm going to determine the derivative of this equation because, again, as I had said earlier, that's going to help me figure out what those critical points are. Okay. Now the critical points in that you're determining, they essentially tell you where the slope, you could say, the slope of the tangent line changes signs. Okay, so for example, okay, if I have something going like this, okay, once I determine the derivative of this equation, okay, I'm going to be able to determine, well, when that derivative is equal to 0, I'm going to be able to determine what the turning point or the critical point is. Okay. Now, when you have a parabola like this, the critical point is going to be this tip right here. Okay. And that, in this, at least in this case that I'm showing you here, that's going to be a local maximum. Okay. Now, the reason that this is a critical point and the reason we're going to be able to, I guess, tell that is because of the fact that the slope of the tangent line at this is 0. Oops. Okay, so this is a straight horizontal line. Okay, the slope of the tangent line at this point is 0, and that's exactly what we're determining when we determine the derivative. Okay, so when we determine the derivative of an equation, we're getting an equation for the tangent line, and that equation is going to be a function of x, and then you're going to be able to input values of x into this derivative and figure out what the slope, the slope of the tangent line at those points is going to be. Okay? So, like I said here, the derivative of our equation is going to be equal to 0 at critical points. Okay? So we want to figure out what are those critical points. Okay? So, if f of x, well, it's f of m in this case, right? If f of m is equal to the equation that you see here, 15 minus 9 over 2, m minus 25 over 2m. Okay, so if this is f of m, then we're going to determine the derivative of that. Okay? Because then we're going to set that derivative equal to 0, and then that's going to help us figure out the critical points. Okay? Which is essentially going to be the local maximum or the local minimum. Okay? So, all right, so when we're determining the derivative, we know that the derivative of a constant is just going to be 0, so I'm just going to ignore that. We know that here, with the power rule, the 1 up here is going to drop down. You're going to have m to the power of 0. That's equal to 1. So the derivative of this guy right here is just negative 9 over 2. Okay. And then finally with this guy right here, well, this is a fraction. Okay. And I'm going to tell you, just be careful with this. You are going to absolutely have to apply some form of rule. Either you can flip this guy up into the numerator, but be sure to add an exponent -1 to that when you do that. And then you can apply the product rule for determining the derivative of that term. Or you can just, I guess, leave it as is and then use the quotient rule. Now, if you forgot what the quotient rule is, here is briefly what the quotient rule means, or looks like. Okay, so it's telling you that if you want to determine derivative of a fraction, you're going to have to determine the derivative of the numerator part of your fraction and multiply it by the denominator. And then you're going to subtract by the numerator multiplied by the derivative of your denominator. Okay? And then you're going to take all of that and you're going to divide it by your denominator squared. Okay? All right, so that's what I'm going to do. First of all, notice this negative right here. I'm going to drop him down right here. Okay, and then I'm going to open a bracket because now I want to evaluate what is the derivative of 25 over 2m. Okay, so according to this, I have to take the derivative of my numerator. Well, the derivative of 25 is just going to be 0. And then 0 times 2m is just 0. So out here, I've got a 0. Minus, okay, so this negative right here. And then f, which is 25, times the derivative of 2m. Well, again, m to the power of 1, okay, you drop that 1 down, so it's now 2 times 1, which is just 2. You now have m to the power of 0, which is just 1. So this is just an outcome of 2. The derivative of 2m is 2. And then you want to divide by g squared. Okay, so you want to divide by 2m squared. Sorry, careful. 2m squared, 2m in brackets, okay? Not just 2m and then to the power of 2. That's wrong, okay? 2m times itself comes out to 4m squared. Okay? Okay, so here's an expression for my derivative, but obviously you can definitely go ahead and simplify this a lot more. So the derivative is going to be equal to negative 9 over 2. Let's go ahead and simplify what's in the brackets here, okay, or in the parentheses. I've got a minus and then another minus. Okay, so this is 0, negative 25 times 2, so I know that up here in the numerator I've got a negative 50, but then I've got a double negative, right? Negative, negative 50, so that comes out to a positive. So what you've got here is plus 50 over 4m squared. Okay, perfect. Okay, so now I'm just going to go ahead and circle this because this is now the equation of the derivative of this equation. Okay, so this is the derivative of this guy up here. Okay, or rather of this guy up here that we had simplified. Okay, now we had said that the derivative functions are equal to 0 at critical points. Okay, so if I want to figure out what the critical points are for this, I'm going to have to set f derivative m equal to 0. Okay, and then I'm going to have to solve for m, because then that's going to tell me, okay, at what value am I getting those critical points? Okay, at what value of m am I getting those critical points? Okay, so that's what we're going to do. You're going to set this guy to 0. Okay, and then you're going to just, well, solve. So negative 9 over 2 plus 50 over 4m squared. Okay, now obviously that means just 9 over 2 equals 50 over 4m squared. Okay, I can multiply by 2 on both sides just to get rid of this guy down here. If I multiply by 2 on this side, well, I'm going to get 9. And if I multiply by 2 on the other side, well, I'm going to get 100 over 4. Well, 100 over 4, that's 25. So 25, and then careful that you don't remove the m squared from where it is. Okay, that m squared is in the denominator, so don't make that mistake. Common mistake of just bringing it up and kind of forgetting it's where its original place was. Okay, so this is m squared. Okay. And then some simple cross multiplying, getting this m squared up here, sending the 9 down into the denominator. So 25 over 9. Okay. And then, well, you want to square root, right? That's going to be the last little bit here. I guess you could have also just kind of, m squared minus 25 over 9, and possibly actually that may have been the more acceptable format. You know what? Let's just do that. I don't want you guys to I don't want you guys to pick up like bad habits like this. Just because like okay, I don't want to be like I know what I'm doing, but I know what I'm doing. So but I don't want you guys to just kind of pick that habit up. So, okay. Let's say m squared, what were we saying? M squared minus 25. Oopsie. 25, that's a 2, over 9. Okay, and then that's equal to 0, right? Well, then you can factor this. Okay, you can get this out as m minus, well, 5 over 3 times m plus 5 over 3. Okay, so then this is equal to 0 at two values of m. Okay, this is equal to 0. Sorry, I'm just going to write it up here. This is equal to 0 at m equals plus or minus 5 over 3. Okay, now here's the thing. What did we just determine? We determined critical points. Okay, that means that we determined points in our graph and of our area, okay, of this guy right here, where if you've got something that looks like this, oh, by the way, this definitely doesn't look like that, but just, heads up. If you got something like this, these values that we're determining what's happening here. Okay, we're determining where is the value of the derivative. So where is this tangent line? Sorry, this is supposed to touch. Where are these tangent lines equal to 0? Okay, that's what we're doing here. Okay, now we've determined that they're equal to 0 at two possible places, plus or minus 5 over 3. Okay, now if you'll think back to our first slide, we've actually already determined that m is actually going to be negative. Okay, m has to be negative, right? Because that way we get that negative slope, and we actually get like a defined, I guess, quantity of area that's cut off, right? If m is positive, that doesn't work out too well, okay? Because then you don't have that defined value or that defined amount of area that's cut off, okay? So I can actually already, just from what we've determined at the start here, I can actually already tell, well, I'm probably just going to ignore the positive 5 over 3. And I'm going to concentrate on m equals negative 5 over 3, okay? You could also, I guess you could also like show that that's not right. You can apply the first derivative rule or the second derivative rule. It really depends on, I guess, on what you want to do. I think this video is getting quite long, so I was thinking maybe I was going to go over both, like the first derivative rule and the second derivative rule with you guys, and like, I guess I could. I don't know. No. Okay, we'll see. Let's see how I'm going to feel in the next few minutes. M equals. Okay, now we just said it should be negative 5 over 3, okay, because we'd already established at the start that the slope has to be negative, okay. Now, what you could do is you can use the first derivative rule, okay, and essentially, okay, so essentially what the first derivative rule is telling you, it's telling you that if you approach this value of m from the left, okay, from the left on your, and this is on your equation for the derivative, okay? So maybe I'm just going to rewrite that equation here since we're going to have to use it anyways. Okay, so here you've got f of m, f derivative of m equals negative 9 over 2 plus 50 over 4m squared. Okay, so essentially here's what the first derivative rule is telling you. It's telling you that if you approach this critical point, okay, so if you approach this critical point and your slope, the slope of this derivative, or the value of this derivative, which is a slope, goes from being a positive slope to a negative slope as you approach this point, m equals negative 5 over 3 from the left, and then if that left part, you could say, is a positive slope, and then you pick another point that's to the right of your critical point, and then you find out that the value of the derivative function at a point to the right of the critical point is a negative, that means that you actually have a maximum, okay? That means that you've got something like this happening, okay? So to kind of show you guys this, if this is your critical point, and you pick up an x value, or rather an m value, that's to the left of negative 5 over 3, and you plug it into your derivative function, and you get a value that's positive for that derivative function. Okay, so let's say this is like a point that you picked here. That's what this looks like. Okay, it tells you that the line that's tangent to that point is positive. Okay, and if you pick a point to the right of your critical point, you take that value and you plug it into your derivative function, and you get a negative answer. That's because the tangent line to that at that specific point is negative. That means it's going down. Okay, and that tells you that this is a local maximum. Okay, so maybe I'll write that down. So that's going to be a local maximum. Okay, so that's from the first derivative rule. Now, obviously, the inverse is true, right? If you're picking a point to the left of your critical point, you plug it into your derivative function, and you get a negative value. It tells you that the slope of the tangent at that point is negative, and that if you pick another point that's to the right of negative 5 over 3, and then you plug it into your derivative function, and you get a positive answer, well, it tells you that the slope there is positive, right? Well, that happens like this. Okay, so if this is your critical point, and this is one of the points that you picked that's to the left, well, you're going to get a tangent that's negative, or a slope that's negative. Okay, same here. Okay, if you pick a point that's to the right, well, you're going to get a tangent line, and the slope of that tangent line is going to be positive. Okay, so that's the first derivative rule. Okay, so you know what? Just I guess for just to be comprehensive, let's just go ahead and do it. This is going to take forever. But yeah, okay, let's just go ahead and do it. The good thing is we don't have to do this again for 5 over 3. Although if you didn't know, like if we hadn't established at the start here, like we had here, that m had to be negative, and you didn't know, then you would absolutely have to do the first derivative rule test, or the first derivative test really, with the value of positive 5 over 3. Okay, so now just to make this simple, let's say so this is my value of negative 5 over 3. Okay, so what's a value that's to the left of that? Okay, well, a value that's to the left of that could be negative 6 over 3. So I'm going to use negative 2, okay, as a value to the left. Okay, I'm just going to circle that just to kind of, highlight that. Now, a value that's to the right of negative 5 over 3, while keeping in mind that technically your other critical point would have been 5 over 3. So what's a value between negative 5 over 3 and 5 over 3? Well, you could actually go ahead and go with 0. Okay, so we're going to go with 0 on that one. Actually, no, let's not go with 0, because that's going to give us something of a headache because of that dividing by 0 on this end here. Let's go with something like get rid of this. Let's go with, I don't know, what we said, 5 over 3. Let's just go with 1 then. Okay, so 5 over 3 is bigger than 1. Okay, so that's good. All right, so let's evaluate this derivative function at those values. Okay, so negative 2. Okay, so if negative 5 over 3 does in fact yield a minimum area, okay, so if it does in fact yield a minimum area, okay, then I'm expecting that my answer here better be a negative. Okay, I'm expecting that when I plug in negative 2 in place of m in our derivative function, we're going to get a negative answer, aka a negative slope. And I'm expecting that when I plug in this 1 on the into our equation on the right hand side of negative 5 over 3, we're going to get we're going to get a positive answer. Okay, because a negative slope and then a positive slope around a critical point tell you that that critical point is a minimum. Okay, so this right here would be a minimum. Okay, so let's just do that. So negative 9 over 2 plus 50 over 4. And then m squared, well, that's going to be negative 2 to the power of 2. Well, negative 2 to the power of 2 is, well, just 2. What? Negative 2 to the power of 2 is just 4. My apologies. It's just 4. Okay? So then this comes out to negative 9 over 2 plus 50 over 16. Okay? Okay, so I guess let's just multiply this by 8 and get that common denominator thing going. So multiply top and bottom by 8. When I say multiply by 8, I mean multiply by 1, right? I'm multiplying the numerator and the denominator by 8. Really, I'm multiplying by 8 over 8. Basic stuff, so you guys know this already. Okay, so this is going to be negative 72 over 16 plus 50 over 16, and you guys are already seeing that this is going to come out to a negative answer, which is exactly what we expected, okay? We don't actually care what that answer is. We just care that it's negative, okay? Because that answer being negative tells us that this is happening, okay? It tells us that this is a negative slope, okay? That our equation, or that the slope of the tangent at that point is negative, aka that tangent line is going down, okay? Now, that was for the I guess the value to the left of negative 5 over 3. So let's do the value to the right of negative 5 over 3. Now, in this case, we have to get, what had we said, 1? We have to get a positive slope, okay, or a positive answer. If we don't get a positive answer, then we messed up getting our critical point, okay? So if that answer is still negative, then this was definitely not, like a local minimum or maximum, okay? That just means that we messed up our critical point. We'd have to go back and check our work. Okay, so, just like things like that can kind of help you see if you've made a mistake somewhere along the road or not. Okay, so let's plug that in, negative 9 over 2. Okay, now plus 50 over, okay, so 50 over 4 and then 1 to the power of 2. Okay, well, 1 to the power of 2 is just 1, so this is just 50 over 4. Okay, well, we're going to multiply top and bottom by 2. For this guy right here, we have negative 18 over 4, okay, plus 50 over 4, okay? So, well, at that point, you just add the numerators together. You get 32 over 4. We don't really care what that value is, right? Again, we don't care what the value is. We just care that it's positive, right? We're happy that it's positive, negative. Because this tells us that around our turning point, this guy right here is negative. The slope of the slope of the tangent at that point is negative, and then we get a tangent that's positive. Okay, so then we get this happening. Okay, so here we've just confirmed using the first derivative, I guess, test or rule or however you want to call it, we just determined that negative 5 over 3 is a minimum. Okay, and that's really, really good. Okay, that's really, really good. All right. Okay. Now, yeah, I guess let's just keep going, right? Actually, no, you know what? Let's do the second derivative test. Yeah, let's do the second derivative test. Should we do yeah, let's just do the second derivative test. Okay, let's do the second. I'm actually trying to convince myself more than you guys. Okay, so let's do the second derivative test. Okay. So, first of all, let's just determine the second derivative first, and then we'll talk about what that means. Okay. So we're going to determine the second derivative of, and you know what? Maybe I'll actually just rewrite my equation again here. The first derivative equation. Okay. Negative 9 over 2 plus 50 over 4m squared. Okay. And let's go ahead and just determine what is the second derivative of this function. Okay. We're going to use the quotient rule again. Okay. In case you've forgotten, maybe I'll just rewrite it here for you guys. Okay. It tells us that if you've got a fraction and you want to determine the derivative of that fraction, well, you're going to have to determine the derivative of the numerator first and then multiply it by the denominator. And you're going to have to subtract by, well, the product of the numerator times the derivative of your denominator. Okay, and then all of that over denominator squared. Okay, so that's just in case you forgot it. And that's the quotient rule, and that's what we're going to apply here. Now, determining the derivative of -9 over 2, well, that's just 0, right? Because again, like I told you, any constant term has a derivative of 0. Okay, so what you're really looking at here is this guy right here, 50 over 4m squared. This is the one that you want to apply the quotient rule to. Okay, so the derivative of our numerator, well, the derivative of 50 is just going to be 0. And then 0 times anything, well, in this case, it's going to be times 4m squared. It's just going to be 0. Okay, so I know that this comes out to 0. Minus f, okay, which is the numerator, so 50, times the derivative of our denominator. Well, our denominator is 4m squared, so you drop the 2. So you now have 4 times 2, which is 8m to the power of, and then you subtract one of the exponents, or just an exponent, you subtract 1. So now you have 8m to the power of just plain and simply 1. So you're going to multiply by, like this guy right here, which is 8m. Okay, and then you're going to square, or you're going to take the square root of 4m squared. Okay, that means 4m squared times 4m squared. Well, 4m squared times 4m squared is going to be 16m to the power of 4. Okay, maybe let's go ahead and simplify this a little bit. So up in the numerator, we've got -50. And you know what I'm going to do? I'm actually just going to say -50m. And this 8 up here is going to cancel out with an 8 down here. And I know you're looking at this and you're like, what? This is a 16. Well, remember that 16 is 2 times 8, right? So I'm going to cancel out the 8 up here with an 8 down here. I've got a 2 still left down here. Okay, so 2m to the power of 4. Okay, well, that's going to be equal to, well, that's -50 over 2. That's -25 over m cubed. Okay, so this is really neat. We've just figured out the second derivative of, well, of our equation of the area, right? That second derivative is equal to what we just wrote over here. So -25 over m cubed. Okay. Now here's the thing with second derivative. Is that it? Oh yeah, that's cubed. Okay. So here's the thing with second derivative. If your second derivative function is greater than 0, then this tells you something about the concavity of the, I guess you could say the region of that region right there. Okay, it's going to tell you it's going to give you information about the concavity of the area situated around M. Okay, and what that means, well, maybe you're like, what the heck is concavity? Well, it tells you if it's concave up or concave down. That's exactly what this means. Okay, so the second derivative test enables you to determine if at a particular point on your equation, if it's going to be concave up or if it's going to be concave down around that critical point. Okay, and here's the thing. If the second derivative is positive, then that tells you that it's actually concave up. Okay, around your turning point. And that means, critical point, around your critical point. And that means that your critical point is a minimum. Okay? Let's do that again. Second derivative test. Now, again, recall that we would have actually done the second derivative test with plus 5 over, what was it? What do we have? Yeah, -5 over 3 and plus 5 over 3, right? We would have determined that. Or we would have done the test with those two, because then that would have helped us to isolate, okay, which one is the right answer. But in this particular case, just because we already knew right from the get-go that the slope had to be negative, we already could just kind of, ignore the other one. But I still did the first derivative test just to show you guys, just to prove that -5/3 was a minimum. And now we're doing the second derivative test just to prove again, and I guess just to show you this method as well, just to prove again that -5/3 is a minimum. Okay. Now guess what? If the second derivative, okay, function about your point M, about that critical point, is smaller than 0, well then that tells you that the concavity of this is facing down. And if it's facing down, that makes your critical point a maximum, okay? Which doesn't really make sense, okay? Again, that's why we ignored that maximum. You can't have a maximum area with a positive slope just because the maximum area there would just be infinity, like going to infinity, right? So that wouldn't make sense, okay? Okay, so what we want to do is we want to see, is this, we want to prove, is this, oops, that's a 3. Is this in fact greater than 0? Okay, because if it is, okay, if our second derivative function at m equals -5/3, if this is equal to a positive value, then that means that we do in fact have a minimum at m equals -5/3. Okay, so let's check it out. Well, we're going to plug this value of m into our second derivative function, -5/3, and I don't even need to go and evaluate this. Okay, some of you guys are thinking, oh, we absolutely have to go and evaluate this, get a value, get an answer, and then look at that answer, and is it positive or negative? You don't even have to do this. You see that the numerator is negative, right? -25. You see down here that you've got a negative, but then that cubed, right? Well, a negative times a negative is a positive, right? So if this was a squared, if this guy was a squared, then this entire denominator would have been positive. But because you're multiplying by another negative, right? So that negative times negative is a positive, right? But because you're multiplying by a third negative, well, then your answer down here is going to be negative. And guess what? Well, you should know this by now. A negative divided by a negative gives you a positive answer. So yes, -5/3 is in fact a minimum. We went and figured it out, and we went and proved it using the first derivative method and using the second derivative method. Now, we're not quite done yet, okay? Like, now that we have the slope, we're happy. Okay, this is where things get really, really simple. We're literally like 30 seconds away from finishing this. Okay, this is where things get really, really simple. Remember back here, we had the point. We had 3, 5. Okay, and now we have the slope of the line. The slope of the line is -5/3. Well, things just got really simple. You can just go ahead and use this right here. So this is the slope point format, okay, of a linear equation. You can go and use this little guy right here to go and figure out what is going to be our final equation, okay? So y minus the provided value of y of a point on that line. Well, that's going to be 5, well, 3, 5, right? So that's going to be 5. Equals, okay, and the slope we've already established is going to be -5/3, and we've even checked it twice using the first derivative method and the second derivative test, okay? X minus, okay, and then x1 is going to be the value of x of that point, which is 3, okay? So now you have y minus 5 equals -5/3 x, and then -5/3 times -3, well, that's going to be a positive answer. And that 3 is going to cancel out the 3 down here, so you got a positive 5. Okay? And you're going to add this 5 over onto this side just to completely isolate that y and to get your final answer. And here is your final answer, -5/3 x plus 10. Okay? Okay, guys, so that's pretty much it. This was actually one of the more challenging questions that I gave you guys. You know, how this is absolutely a question about optimization with calculus. Like, how do you use calculus to figure out, what is the minimum or the maximum value and be able to optimize for a particular situation. Anyways, hopefully this was helpful. If you have any questions, don't hesitate to ask them, I guess, in the comment section below. All right, take care, everyone. Bye bye.